Okay, one more application of the differential. Suppose that automobile position as a function of clock time is given by this function, s of t equals 2t squared plus 4t plus 10, where s, position s, is in meters, when t, the clock time, is in seconds. Now, I'll just make a side note here that implies that the way to actually write out s of t so that s comes out in meters when t is in seconds is to put units of meters over seconds squared on the coefficient that multiplies t squared, so that when you multiply by t squared in t in seconds, you're going to get seconds squared here to divide the seconds here, leaving you meters, which is what your position had better be in. And similarly here, t is going to be in seconds, so you want to have a coefficient meters over seconds here, so the seconds will divide the seconds and leave you meters that can be added to the meters you get here. And you'd better have this in meters so that all three terms here are like terms that add up to the terms in the units that we need for s. And that's worth knowing, but that's kind of a digression. So you might want to come back and try to understand that, because it's often a point of confusion when you see something like this. But there's a simple explanation of why these units are what they are and where they are. Okay, now, the question we want, though, in terms of this, and we'll probably, I don't know, I'll probably just go ahead and use this and wave my hands rather than confusing the issue with this notation. And we'll take care of that later. Okay, change in position in terms of t and dt. Okay, where t is some time and dt is some time interval. Okay, well, that's just a straightforward application of the derivative. It is an application of the derivative, but more specifically the differential. ds of t is going to be what? It's going to be s prime of t times dt. So there we have it, except of course we've got to do our s prime of t. Okay, so we can write that out, ds of t, s prime of t, very easy derivative. We're going to get, I'll probably mess it up, but okay, we're going to get 4t plus 4. Okay, and you know, in units, that'd still be 4 meters per second squared and 4 meters per second there. So you know, that's what you're going to get. And that's multiplied by dt. Okay, so let's apply this to a specific case. Let's say at t equals 10 seconds, what is ds if dt equals 0.4. I think too many 4's in this. I'm going to change that. We'll make that 0.6 seconds. Well, the solution is just a matter of actually plugging this in, but then we want to think about what it all means. So, well, ds of 10 seconds, and I'll suppress the units here. We'll worry about units a little bit more later. ds of 10 is going to be what? 4 times 10 plus 4 multiplied by 0.6. And if we do that, we get 44. 44 times 6 is 264, so that's 26.4. And that's going to mean 26.4 meters, as we could verify if we got a little bit more specific about our units. Okay, so it means we're going to go 26.4 meters in that 0.6 of a second. And that's moving along pretty fast, because 30 meters in a second is about 70 miles an hour. Okay, now let's think about what this really represents now. What does the derivative of a position function tell us? Well, we should understand from calculus that the derivative of a position function with respect to time is a velocity function. So and let's say exactly what we mean by this. This is the rate of change of the position S with respect to the clock time T. And that is exactly what we mean by velocity. That's exactly a definition of velocity. Okay, so that's how fast and in what direction are we moving. We're moving at, in this case, 4t plus 4 came out to be 44, and that would be 44 meters per second. If we keep these units when we do everything, it comes out in meters per second, because we have, this is 4 meters per second squared, meters per second squared coming from the coefficient here, multiplied by t in seconds. That's going to be 40 meters per second when t is 10 seconds. Okay, and that's going to be in meters over seconds, because it comes from here. So the units do come out meters per second. So for all these reasons, we not only know from the definitions, but we understand with some depth that this has to be a velocity. So if that's the velocity, then if we multiply a velocity by a change in clock time, we're going to get the change in position. So we have change in position. So what we have here is actually evaluating this calculation has the same meaning as 44 meters per second multiplied by 0.6 seconds equals 26.4. It's got to be meters because it's a change in position. And that's exactly the way the units work out. Now another observation, this is a quadratic function, okay, and it's got a positive coefficient of t squared, so it's concave up. That's a pre-calculus understanding of this quadratic function. And yeah, well, that's it. That's good. So, as in the previous example, that means that our differential approximation, 26.4 meters, is a little bit low. So, concave up implies the differential approximation is low. So if we evaluate the position at 10 seconds and then at 0.6 seconds later, 10.6 seconds, we're going to get the actual change that we can compare with our approximation. We can also take our second derivative, which is 4, and use it to estimate by how much we would be high here. We've seen that before. We're not going to go that deep into it, but you should know that we can do that. Okay? So what we're going to do is, well, I'm going to do the calculation off screen. It's easy to calculate this for t equals 10. That's going to be 200, that's going to be 40, and that's going to be 10, so that's 250. So we have S of 10 equals 250. S of 10.6 equals what? Well, I don't want to do all that calculation in my head. I can square 10.6, but then I'm going to start double it, but then I'm going to start losing track of things. So I'm going to cheat and use a little machinery here. Okay, so S of 10 is 250. S of 10.6 is about 274.7. So that delta S, change in S, is the difference here, and that's very easily seen to be 24.7. And incidentally, this is one of the reasons why we use a ds here and a delta S here. This is the actual change. This is what we're using for the approximate change, the ds. Anyhow, our delta S is 24.7, and we see that's about 1.7 units low, and that's about, 7% low, I think. Okay, so we do have some discrepancy here because of the concavity of the graph. Once more, I hope you pull this all into a nice, neat little bundle and are prepared to use it. Life will be much simpler if you are.